All right, so we're recording now. Actually, you know what? I'm gonna head back to last week's slide since I just remembered we need to review that thing, right? Hopefully everybody else remembered. Hold on, here it is. So I'll open up last week's slides and then I'll do that last problem really quick. Today's code is, hold on, electron 42. Electron 42. All right, so if I just spam the right arrow to get to the last slide, there we go. Come on, let me annotate. There we go. All right, so we covered like the basics of this, right? I'll just write it out really quickly without going through it as deeply. But our first step whenever we're given a problem that's written in words and we don't get an equation is that we have to make the equation ourselves. So since I explained like the logic behind that last time, I'll just like kind of speed through it right now. So that's our equation. And then we're given mass amounts of like the chemicals we're reacting. So what we need to do with masses is we need to convert them into moles because that's the universal unit of like stuff or amount, if you want to think about it that way. You can't compare grams, you actually have to compare moles if you want to get like accurate ratios. So for example, we're looking for a 1-to-2 ratio between this and this because that's how it's described in our equation, because you can imagine like an invisible 1 right here. We just don't write it down. So in order to convert from mass, which is in units of grams, to moles, you have to find the molar mass of whatever you're working with. So you would set up like, this is called dimensional analysis. You would set up the multiplication for your grams and grams to cancel out, and then you would get left with units of moles. But in order to find out like the actual number of moles, you would have to reference the periodic table. This one I'm just gonna do from memory. So on the periodic table, I'm not gonna pull it up right now, but calcium is 40.078 grams per mole. Oxygen is 16.00. And then hydrogen is 1.008. So if I add all of those up for CaOH2, that's 40.078 plus, we have 2 oxygens in here, so we have to multiply that by 2, and then we have to also multiply the number of hydrogens by 2. So if I do that really quick on my calculator, we get, this is going to be to the hundredths place because the oxygens, the oxygen's molar mass is only accurate to the hundredths place. So if we add, we need to apply our sig figs to the hundredths place. So that would end up being that value. Then we get 74.09 grams per moles. And then if we do 22.9 divided by, so actually the exact molar mass is 74.094. So you want to be using exact values when you do calculations. You just want to like write them down, applying sig figs. So if I do that division, then I get 0.309 moles of CaOH2. And the reason I cut it off at the thousandths place is because that's 3 sig figs for this number, and this is like technically multiplication, right? So it's 3 sig figs, and then this is 4 sig figs, so you would have to go with the less accurate one. And then for the 10 grams of HCl, hydrogen, just as a reminder, is 1.008 grams per mole. And then Cl, or chlorine, is 35.45. So if you add that together, that's your exact sum. And then if you apply sig figs, this becomes 36.46 because this is to the hundredths place. So I'm just going to set up like the same exact format again. And actually, instead of calling this 10, I'm going to say 10.0, just so we have a reasonable amount of sig figs. So 10.0 grams. And then we put the molar mass here. And then if we do this division, then it comes out to 0.274 moles of HCl. So now what we do is we know the amounts of each, so we just have to compare them and figure out which is going to run out first. Because in this case, obviously there's not some like super great ratio between the two, right? Like if I clearly saw that there was like, for example, 5 times more HCl, it would be a lot easier to do like mental math. But in this case, we have to do some stuff by hand. But one thing we can just do by comparing is we realize that HCl has to run out first here. And the reason for that is if you just compare these two numbers, obviously 0.274 is a lower number, right? But if we look at the equation up here, I need twice as much HCl as I do CaOH2. And if I already have a lower amount of HCl, there's no way I'm going to have twice as much, right? So I know that HCl is going to run out first, so I can apply that as my limiting reactant. So if I erase some stuff just so I create like workspace. I'm going to use the full amount of HCl because I said that's going to run out, right? So if I use this much HCl, I'm going to be left with none. I'm just writing this off to the side to like keep track, right? And then I'm going to use half of that amount of CaOH2 just because they're in a 1:2 ratio again, right? So if I use 0.274 moles of HCl, or whatever that is divided by 2, so divided by 2, that's equal to 0.137 moles of CaOH2 that are going to be used. So if I want to find out what's left at the end, I can just do subtraction, right? So 0.309 minus 0.137 is equal to 0.172 moles of CaOH2 left over. I'll just write that so we know. And then the end goal of this is to figure out what our end pH is. And you can like open up last week's slides if you want to look for the pH formula. But basically here, what we need is we need to figure out some kind of concentration. We can either figure out H plus concentration or OH minus, but either way, we can get to pH from that. In this case, obviously, OH minus is going to be a lot easier because it's included in the chemical that we're working with, so we don't have to take extra steps. So in this case, we have to do a tiny bit more stoichiometry because we know that 0.172 moles of CaOH2 are left over, but for every mole of CaOH2, this 2 is telling us that there's 2 moles of OH minus. So basically, I have to multiply this number that we just got by 2 in order to figure out how many moles of OH minus, aka hydroxide, are in the solution that we have. So 0.172 times 2, we get 0.344 moles of OH minus in solution. And then one of the formulas we had on this particular slides, so this will be last week's slides, is that POH is equal to the negative log of the concentration of OH minus. And how we find concentration is that we take moles divided by the volume. And we actually have the information that the volume is 35 milliliters. And when you divide by the volume to get the concentration, you actually have to have the volume in units of liters because you basically like the capital M is the unit for concentration or molar. And this is the same thing as moles per liter. So if we do 0.344 moles, that's coming from this number down here, divided by 0.035 liters. That's just a quick conversion.
How do you get 0.344?
It's because, so did you understand up to this part how we subtracted how much we used so that we can figure out how much is left?
Yeah, I heard you that part, but like I was away for a bit.
Oh, okay. Yeah, so it's pretty simple. It's just that we ended up with 0.172 moles of this particular thing, CaOH2 left over, but we can see by the 2 in the bottom that for every mole of CaOH2, we actually have 2 moles of the OH minus that's inside of it.
Okay.
Yeah, so we just multiply this by 2 in order to figure out how much OH there is, which is how we got 0.344.
What about the used ones?
The used ones, it turned into water and CaCl2, which basically we're talking about like our end goal is to figure out the pH of the solution after this reaction completes, but these actually don't affect the pH of the solution. So we can kind of just like forget about them.
Why does it not affect the pH?
So water is just water, right? So that one's pretty simple. It's just neutral, so it's not going to do anything. And then CaCl2, if you like slightly remember this from last week's, we didn't really get into like why metals don't affect it or like why certain metals don't affect it, but just like assuming that Ca2 plus, which is the form of calcium that's in here, doesn't affect it. The reason why Cl minus doesn't affect it, which is the form of chlorine that's in here, is because it's the conjugate base. If you remember what that is, it's just taking an acid and then like removing the
Oh, yeah,
hydrogen.
I know that one.
Yeah, it's just the conjugate base of a strong acid. So when you have that case, then it doesn't affect the pH. But yeah, it's kind of a lot to
Okay.
like remember. So you can always like go back and reference.
Okay, so what are we doing with like the like the 0.344 thing?
Oh yeah, so we found moles, and then because this formula for pOH has to do with concentration, we have to convert moles to concentration. So we have both moles and volume. So all we have to do is divide them in order to get the concentration value. So
Wait, why do we need the concentration log? Can we just like times negative log to the 0.344 thing and then get like the pOH, and then like from that you minus, just from that just find the pH?
yeah, that's basically it. But you see these brackets, right? Like it's not parentheses, it's brackets.
Okay.
Yeah, because like parentheses are like curved and brackets are like cornered, right?
Yeah.
Yeah, the reason you put brackets is you're telling everybody you're dealing with concentrations. So like that's what the brackets in that case mean. So that's why we know that we need the concentration specifically in order to like use this formula.
Oh, really? Oh, okay.
Yeah. So yeah, if we do that division, it comes out to 9.82 molar, which is actually like a huge concentration. I just came up with random numbers for this problem, so it's not going to be like super realistic, but that means we can do pOH is equal to negative log of 9.82. And that, okay, you know, this is going to kind of blow your minds a little bit because the pOH is, if I clear everything, the pOH comes out to negative 0.992, which is weird, right? Because we've always thought of like pH and pOH as being positive numbers 0 to 14, but you can actually have negative numbers or numbers bigger than 14. It's just that you wouldn't usually encounter it. But I guess like the random numbers I chose didn't really pan out. But
does it mean that it's like very acid or something?
in this case, it means it's very basic because remember how on the pH scale, like as you get closer to 0, it's more acidic.
Yeah.
Yeah, so
yeah.
it's the reverse for pOH because OH talks about basic stuff and pH talks about acidic stuff. So you can talk or you can think about the pOH scale as being the exact same thing as the pH scale, but for bases. So the lower your pOH gets, the more basic it gets.
Okay.
Yeah. So we also had this formula on last week's slides. It's just like addition. So you can plug in pOH here to get pH. So if we just substitute, and you don't have to worry about sig figs in this case because 14 is an exact number and that doesn't affect your sig figs. So then your final answer would end up being 14.992, your pH. All right, yeah, that was kind of a lengthy explanation, but we'll get to this week's stuff now.
Wait,
yeah, so,
but doesn't like
Excuse me? I have a question.
Oh, sorry, can I hear Angela's first? I'll get to you in a second.
Okay.
so like you got the pH as like a bit more than 14, but like doesn't the pH only stop at 14?
Yeah, so that's what I was talking about. I picked some kind of bad numbers because the reason it's taught like in school that pH goes from 0 to 14 is because that's for like real life. And the numbers I picked don't really work for real life. So you actually can go past 0, go into negative numbers, and go up past 14, but it just won't really happen in real life. That's why. All right, so getting to this week's slides. All right, today's all about gases. So yeah, we'll just get right into it. So kinetic molecular theory is like kind of a intimidating name, right? Oh, sorry, Henry. I almost forgot. What's up?
For pH and pOH, is 7 the mean neutral, not acidic, not alkaline or basic, whatever you call that one?
Yeah, both. Either scale you're using, no matter if it's pH or pOH, 7 is always going to mean neutral.
So 1 for the pOH scale is very alkaline, correct?
Yeah.
Or basic? What's alkaline or basic mean?
Are you asking like, is there a difference, or what do they
Like,
mean?
what is it basically like? Is it like, what is it? Is it acidic or something
So acidic means there's a lot of hydrogen ions. That's basically the definition. And then the opposite of hydrogen ions are hydroxide ions, which is the OH that we were working with. So when something's alkaline or basic, that means there's almost no hydrogen ions and a lot of hydroxide ions. It's basically
What's
the
the
opposite
taste?
of acidic.
Is the taste sour or sweet?
I mean, don't taste stuff to find out, but usually people think of acids as like sour, and people think of bases as
Yeah.
like slippery and like bitter. Like think of soap.
Oh yeah, soap is bitter.
Yeah.
I
All right.
didn't
Soap
taste
is higher
soap
than
though.
7.0.
Yeah, it is. What was that? Sorry.
But I didn't taste soap though.
I don't know. Don't taste it to find out, okay? Just take my word for it.
So then what does base taste like?
Just think of like slippery and bitter. That's the most I can say. Cause like, I'm not saying soap because I've personally tasted soap. People just say that that's what it tastes like. Like, that's just an example people give.
Why do you taste soap?
I don't know. I'm guessing by accident.
Oh, really?
Yeah.
What does it taste like then?
I don't know. I haven't personally tasted it. All right. We
Wait,
can talk
did you
about
say
soap.
you taste
Wait.
soap though?
Huh?
Did you say you taste soap though?
No, I said I've never tasted it, but I'm just like
Soap is
trusting other
disgusting.
people who said it. Yeah, guys, let's move on for now. We can talk about this after class. So moving into kinetic molecular theory, it's like kind of an intimidating name, right? Because it's like 3 big words, but it's pretty simple. It's just talking about how we think about how gases move, or like how individual small gas particles move. So the first part to this theory is that most of the space occupied by gases is empty. It's kind of like atomic theory in that we say that most of the atom is actually empty. It's the same way. So like, I guess a deeper explanation of this is basically that each small gas particle, if you can think of like the molecules, they're small compared to the spaces in between them. So like, say we were on like a football field and there were only like 10 of us and we spread out as far as we could from each other. You can think of it like that. Like, we're small in comparison to like the 10 yards that separates us. Molecules of an ideal gas. So an ideal gas just basically, ideal means like in a perfect situation. So it's basically saying, if we remove all the possible things that could go wrong with this gas, we're describing an ideal gas. So molecules of an ideal gas don't attract or repel each other, and they don't attract or repel whatever container they're in. And then the third part of this theory is that gas particles, or like the molecules that make up the gas, are always in random motion. And random motion involves just moving in straight lines. So like that, and you move until you hit either another gas molecule or you hit the edge of the container and you bounce back. But basically, no squiggly lines, no randomly changing speed. It's just you move in a straight line at the same speed until you hit something, and then you change your direction. And then the fourth part of this theory is that collisions of ideal gas particles are elastic. You really don't know, or you don't have to know what this means, because like types of collisions are much more physics than chemistry, and it's also like high school physics too, so you don't really have to know. But what it means is that your kinetic energy is conserved, and I guess you can kind of just think about it as like if two things bump together, they're going to maintain their speeds basically. Like kinetic energy is going to be conserved. So if they're like the same particle and the same mass, they're going to bump together and they're going to head in the opposite directions with the same speed again. So that goes in line with the random motion part.
Wait, so what is the kinetic molecule theory? Is it like 1, 2, 3, 4, and 5? Or is it
Sorry, can you say that louder? The first sentence.
so like what is the kinetic molecule theory? Because you like said a lot of things and like what is exactly is like kinetic molecule theory all of that or
Oh, kinetic molecular theory?
yeah,
Like what is it?
yeah.
Oh, it's just the name is big, but all it is, it's trying to describe how gas molecules move. That's all it is.
Oh,
Yeah.
okay.
So then number 5, it's just saying that as your temperature rises, the kinetic energy of the gas is, or the gas molecules is going to increase. So kinetic energy, we all think of movement, right? So basically, as your temperature increases, the gas molecules are going to move more like violently. They're going to be traveling at higher speeds. And the reason I say absolute temperature here is because whenever you see absolute, that means we're talking about the Kelvin scale, which is also what that capital K means.
Wait, can you explain number 4 again?
Yeah, sure. Also, like this one, I just included because it's like part of the theory, but it's also like the physics part. So at the end of the day, if it still like confuses you a little, don't worry because it's like pretty much not chemistry. So collisions of the gas molecules are elastic. So that means if I have two gas molecules and they're the same gas, right? So they're going to have the same mass because they're both just one molecule each, and they hit together, they're going to rebound back at their original speeds, just in the opposite direction. So that's like what an elastic collision would mean. All right.
Well,
This one, let's see if I can get the chat open. Yeah, you can just like, I guess like shout out, like not really shout, don't like unmute and shout, but like use the chat to shout out an answer here. This is really just going straight off of the previous slide. So it's just kind of to help us ingrain the information. Yeah, looks like everybody's pretty much getting it. So nice. Yeah, we've got like 7 correct answers already or
He is
something.
wrong.
Yeah, D is wrong, so D is right in this case because it's an except question, right? Yeah. So it says when particles collide, kinetic energy is lost, and we spent like extra time on that bullet point. So luckily everybody remembered. Since it's an elastic collision, kinetic energy is going to be conserved, aka like remain at the same level. So it's not going to be lost.
wait, what does it mean? So
Yeah,
like
what's up?
what does it mean by like that word?
Negligible? Oh, so remember how I did the comparison about like if 10 of us stood out on a football field and spread out all the way? Yeah, so negligible just means like it doesn't compare, like it's nothing compared. Like say there was an elephant on a scale and I put a paperclip on the scale with it. The mass of the paperclip is negligible because it's just so much smaller than the elephant. That's what that means. Do you kind of get a sense of what it means?
Okay, but like then I don't really understand like what this bees are saying.
In simpler words, also like it's okay if you don't understand because this is like a competition thingy. But in simpler words, it's just saying the container or like whatever room it's in is huge compared to how small each molecule of gas is. That's it.
What if the container is small though?
I mean, I guess good like That's a good theoretical question, but it's hard for us to make, as humans, it's hard for us to make the container like that small, right? Because we're talking about atoms and molecules here. So we can't even like see that small to make a container, right?
Okay.
All right, so moving on. These are called Maxwell-Boltzmann distributions. They kind of just look like graphs, but they basically tell us like, or I'll go over the axes first. So if you look at the y-axis, if you don't know what that is, it's the one that's on the left and it's running up and down. So it says probability next to it in both pictures. That's basically telling you of all of the gas particles, like say in the room, of all of the gas molecules in the room, how many of them are at this particular speed. So velocity is running along the bottom, right? So you can see in the left picture that most of the oxygen gas molecules, and we know it's oxygen because it's labeled as O2, we know that most of them are like basically at 400, they're traveling at 400 meters per second-ish. Like it's a little bit less than that, shown by the dotted line. But we can see that there's a variety, right? Because it extends over a wide range of speeds. There's not that many oxygen molecules traveling at like 1200 meters per second, but there's still some. That's what it's showing. So most of them hover around like some sort of middle ground average speed near 400, but there are some like basically not traveling at all close to zero, and there are some closer to like 1,000. But it just shows like the probability. And then the picture on the right shows the effect of temperature. So like we talked about the last bullet point for kinetic molecular theory, as the temperature increases, your average kinetic energy of the gas molecules will also increase with it. So what that means is kinetic energy is about movement, right? That means basically the fastest moving gases in the cooler temperature are not going to be as fast as those gases in the higher temperature. So that means since it says T2 is greater than T1, we know that T2 is dealing with the higher temperature. So that's why it extends to the right of the red curve. The green curve is extending to the right of the red curve. So we know that there are some, we'll call them like green gas molecules that are traveling much faster than the red gas molecules. And it's also like slightly flatter, like the peak isn't as high up, which just lets you know that it's more spread out over a variety of speeds. And this is another Maxwell-Boltzmann distribution, and it's showing what molar mass does. Basically, intuitively, what do we think is going to be faster? Lighter atoms or heavier atoms? You can just say in the chat.
Lighter atoms.
Yeah, exactly. That's how all of us think, right? So this is just like a numerical way to show that. So we can see that here, helium is the lightest, right? We have 4 elements being shown here. We have helium, neon, argon, and xenon. These are all noble gases. But we can see that helium has the widest and lowest curve. So it's basically, it has more spread across all of the velocities, but it also has the most number of gas particles at the higher velocities, right? Because you're going to find some gases traveling at like 2,000 meters per second. Whereas for like, let's look at the purple line. For xenon, it's like impossible to find any xenon particles traveling at 2,000 meters per second, as you can see by the fact that it's flat at 0 there. So that just tells you that lighter molecules travel faster, or lighter atoms, whatever you're dealing with. All right, so you've probably heard this term before, pressure, but for chemistry, there's like kind of a more formal way to define it. So you might think of pressure as like you shaking a soda bottle, and like as you twist off the cap, you can feel like something's pushing it out. Basically, how chemists define pressure is how violent. Violent means like how much force. So like, I guess like throwing a baseball at 90 miles per hour versus at like 50. And then how often the collisions of gas molecules occur. And there are 2 types of collisions. It's the collisions of like gas to gas, and then it's the collision of like gas to the container. So you can think of like an oxygen molecule hitting the wall of your room, for example. So basically higher pressure means that collisions are happening more frequently and they're happening more strongly, aka like more violent or more forceful. And then if you ever need to convert between units of pressure, all the conversions are here. This is just for a reference later. We're not really gonna like go into it. And now we're kind of getting into a bunch of laws. For some reason, like all of the laws in chemistry, besides the really simple ones like conservation of energy, are about gases. So we're gonna learn a lot about those today. So there's first Graham's law of effusion and diffusion. We're not really gonna get into the mathematical side of it. I think, let me see what the practice problem's like actually. Yeah, we don't have to get into the mathematical side of it. But we just want to realize how we can compare speeds of atoms just by knowing their molar masses. So diffusion is a fluid. A fluid means either a liquid or a gas, but in this case, we're talking about a gas, right? So diffusion is when a fluid spreads evenly throughout its container. So I guess think about as you light a candle and then you blow it out, the smoke comes up, right? So that's kind of like the gas that's being released trying to escape and spread out evenly into the rest of the room. And then effusion, or yeah, you wouldn't like pronounce the E like that much, but effusion is when the gas escapes its container. So escaping is different from spreading, right? So say I had a balloon and I like poked it and it didn't just like explode, it just like slowly shrank. That's effusion because the gas is escaping out of that small hole. So there are these equations, but we won't really talk about the math part of it. It's just that for M, capital M means molar mass. So for heavier molecules and atoms or compounds or whatever, they're going to travel slower than lighter ones. That's all this is saying. So knowing that, let's look at this practice problem. Just pull up a periodic table online or like to the side or something, and we'll figure out how to do this one together. Yeah, nice. PhET simulations are actually really helpful for a lot of things, not just chemistry. So in this case, how are we going to figure out which one's the fastest and which one's not? Like what numbers are we going to be comparing here? Or like what measurements, I guess?
How fast they travels?
What was that?
How fast these four gases travels?
Yeah. But we don't have like the data on that, right? So what gives us a sense of how fast it travels? Like yeah, that's the idea.
Molecular weight.
Yeah, exactly. So we look at the periodic table and we basically, we just cover that the lightest one is going to travel the fastest, right? And on the opposite end, the heaviest ones are going to travel the slowest. Yeah. So basically what we're trying to do here, we're just comparing the molecular masses of these things. So I don't know. Somebody tell me in chat which one is the lightest one, and we can just go by process of elimination. Yeah, helium's obviously the lightest one, right? So which two answers can we eliminate right away?
B and D.
Hold on. Okay, wait. Lightest ones travel the fastest, right? So this answer, or like the answers are talking about order of increasing speed, not increasing mass. So trying to
A and
rethink a little.
C.
Yeah, A and C, you got it. And nice, Sonia and Liran got it too. Yeah, so we can eliminate A and C right away. And then we're just stuck looking at B and D, right? And we actually don't need to find the mass of CCl4 because they're in the same spot for both B and D. So what we need to do here is we just need to see whether N2 or CO2 has a greater mass.
Wait, like what is the order? Is it like from highest speed to lower speed, or is it?
So if you look at the greater than and less than symbols in there, it's opening up to the right, right? So that means whatever's on the right of the symbol is greater than whatever's on the left. So basically, as you move towards the right, you want to be looking for the higher speed ones. Higher speed means lower mass.
Oh, okay.
Yeah, so we're choosing between B and D, and yeah, B is right, but can somebody just
B is right.
yeah, but can somebody
B.
give me like the numbers? Can somebody tell me exactly why B is right? Comparing the masses of N2 and CO2. Nice job on getting it, by the way. Hold on, let me get ready to annotate. Oh yeah, you got it, nice. So basically, if we look at the molar masses of CO2 and N2, once again, I'm just not gonna pull up the periodic table, but basically, carbon corresponds to 12.01 grams per mole. Oxygen corresponds to 16.00 grams per mole. And nitrogen corresponds to 14.01 grams per mole. Those are the only three values you need, and you just add up different combinations of those. So for N2, you have 2 nitrogens. So it's just 2 times 14.01, which is 28.02 grams per mole. And then for CO2, you have 1 carbon, and then you have 2 oxygens. So this becomes 12.01 plus 32.00, which is 44.01 grams per mole. So obviously, if we're comparing 28 and change with 44 and change, 28 is a smaller number. So therefore, N2, or nitrogen gas, is a lighter gas than CO2. So that means it's going to travel faster than CO2, and that's why our answer is B. Yeah, nice job on getting that.
Wait, what about the other molecule?
Oh, so are you talking about CCl4?
Yeah.
The reason we don't have to look at that, we're just kind of saving time, is because we narrowed our answer choices down to B and D, right? Because they helium needs to be the fastest because it's the lightest.
Yeah.
But both B and D have CCl4 in the back. So like there's no difference there, right? So instead of looking for the mass of that, we can just skip ahead.
All right. Okay.
Yeah. So it's just kind of saving time. It's not wrong to do it, but I guess it's just like less efficient. So Dalton's law of partial pressures, another thing that's like called a law, but it's kind of like too simple to be called a law in my opinion. It's basically just like addition. So if you have like, say you have all 5 of these gases in your room, and like that's what makes up air, you have oxygen, nitrogen, argon, water, and CO2. Basically, if you add up all the individual pressures that they contribute, you get the total pressure of air. So, you know, it's not rocket science. It's literally just addition, in my opinion. So, yeah, it's pretty simple, and we can move on. So this is like, I guess, starting to get into like the big gas laws, or like the gas laws that people call the actual gas laws. So for Boyles Law, basically like this guy named something Boyle made a law after looking at the properties of gases, and he said that the volume of a gas is inversely proportional, or it varies inversely with the pressure when the temperature and the amount of the gas, aka the moles of the gas or the mass, is kept constant. So basically what that's saying is, if you look at the GIF that we have in there, if you expand the container by like pulling up the piston is like the top wall. So if you pull that up, you're increasing the volume, right? And then what that does is you make the collisions that the gases are having less frequent. You can obviously see that the gas molecules on the right are having like less trouble moving around than those on the left. The ones on the left are just like bashing against each other and the walls, which is why they have a higher pressure. So that's why Boyle's law says that if you increase the volume, the pressure is going to decrease. And if you increase the pressure, the volume is going to, wait, hold on. I mean, that you wouldn't really manipulate the pressure in this case because it's a different kind of container, but we'll get to that later. This is another interactive you can just click on to play around later. There was also, somebody sent a pretty good one. a couple minutes ago to.
Yeah, the PhET simulation actually does have all of these.
Yeah, nice. All right. So you can just like look in the Zoom chat for that too. The next one we're going to look at is Charles' Law, which basically says that the volume of a gas is directly proportional with the temperature. So basically what that means is this graphic, in my opinion, is like not as great as the other ones. But basically, if you increase the temperature, so let's say like you have a jar of whatever gas you're working with. Not a jar, but like a jar, but it has the piston on top. So the volume is like changeable or flexible. And then you like heat it up. You like, say you light a bonfire and you just like put it on top of it. The volume or like the piston is going to expand. It's going to be like a syringe and it's going to go up. And that means the volume's getting bigger because basically what happens when you increase the temperature, if I go to the next slide, it has to do with a different law. It's called Gay-Lussac's law. What happens when you increase the temperature is that, oh yeah, what's up? What's your question?
If you sit on the piston, will still push you up?
I guess it depends on how much you weigh, but you will definitely feel the force going up. It like depending on how much you weigh,
Molecules
it might
kind
not
of
push
push
you up.
up, correct?
Yeah, that's
If
what
there's
pressure
enough
is.
pressure, then you'll get pushed up, correct?
Yeah, if there's a huge amount of pressure, then yeah. All right, so just explaining how this works. So if you increase the temperature, what's going to happen is the molecules start moving around faster. They hit the container and each other a lot more forcefully. So that means the pressure is increasing. And the reason they moved around faster is because temperature is the same thing as kinetic energy, right? And if they're going to move around faster and hit each other faster, then pressure is going to increase. But since pressure increased, the volume has to re-increase in order to lessen the pressure. So like basically it's adjusting and it's reacting to the other conditions. And then Avogadro's law, basically it's talking about the moles of the gas and the volume. It's like probably the most intuitive or like the easiest law to memorize. Basically, if you have more of a gas, so you can think of more as in mass or moles. If you put more stuff of the gas into a container, the container is going to expand to occupy a bigger volume. So it's pretty intuitive. Like if I put 100 balls in I guess like a huge syringe, because like what kind of syringe is that big? But like if I put 100 balls in a syringe, I'm going to need to lift the syringe to a much higher height and use a bigger volume than if I put like one ball in it, you know? All right, so basically, oh, also one thing I just wanted to say. This lowercase n here, I don't think we've worked with it in this class yet, but that's the symbol for moles. And the reason that Avogadro's law is about moles is because Avogadro is kind of the guy that came up with like the mole concept. So if you search up like Avogadro's number on Google, what comes up is 6.022 times 10 to the 23rd. And if you remember from like day 2 or something, that's the conversion for moles. So like if I have 1 mole of apples, I have 6.022 times 10 to the 23rd apples. So that's why it's called Avogadro's law, and that's why it has to do with moles or lowercase n. And then basically if you combine those big 4 gas laws, you get this equation. And the reason, I'll just go through all of these. Oh, and I'll go through what R means too. The reason that pressure and volume are on the same side of the equation is because we said they're inversely proportional to each other, right? So that means basically they move in opposite directions. So say you doubled the volume on the left side, in order to make the equation still equal, pressure has to half, right? So that's why it's on the same side. It's because they have to move in opposite directions, and that's why they're inversely proportional. Whereas we just said that volume and moles are proportional. So that's why they're on opposite sides. Because if you double moles, which is lowercase n, you have to double volume, or you double pressure in order to get the same effect so that both sides are still equal. Same thing with temperature. Was somebody asking a question? I think I might have heard something.
Yeah, I was.
Yeah, what's up?
So you said like inversely proportional, like the volume and the
Pressure?
pressure was inversely proportional. What does inversely means?
So you can think of inverse as kind of like a synonym, or do you know what synonym means?
Yeah.
Okay, cool. Yeah, you can think of it as a synonym for like opposite. So proportional means like if I multiply one thing by 2, I have to multiply whatever it's proportional by 2 as well in order for them to, I guess, like both be multiplied by 2 and both have the same change. But inversely proportional just means proportional in the exact opposite way. So if I multiply like pressure by 2, volume has to be divided by 2. That's why it's called inverse.
Okay.
Yeah. And then I think I've covered everything in this equation except R. I actually kind of forgot to put it on a slide, but I'll just show you like a Google search. R is called the universal, or like it's called the molar gas constant, right? Basically, it's just a constant. It's just there because you have all this proportional stuff, and once you all multiply it out, you actually just like get some kind of number. So when we're dealing with gases, and usually like for our purposes, you'd be dealing with gases in the unit of atmospheres, or ATM. Hold on, let me see if I can find a value. Come on. So you'd be dealing with the unit of ATM. And then here it says 8.3145, but that's not what you would use for ATMs. You would actually use 0.08026. So if you can see the second column, or like first column, second row on this picture here, it says 0.082057. Usually people just shorten it to 0.08206. And then you can see the units there as well. They're not as important. Basically, it's just a random number to help balance the equation out so both sides are equal. That's really all it is. You actually do end up using a lot when you do math with gases, but luckily we don't have to do that. All right. That's kind of the end for today, I guess. Is there anybody that would like me to go back to a specific slide? I'll just like sift through the slides to see if anything like prompts anybody's mind.
Will this slide be like on the Google Classroom?
Yeah, it's there right now.
What is argon?
It's just another element. So, you know, like calcium's an element, argon's just another element, but it's usually found as a gas.
What's it for?
What is it for? I don't know, but it's just like, have you heard of how like air is like 70-something% nitrogen and like almost the rest of it is oxygen? Have you heard about that before?
Yeah.
Yeah, there's like 1% argon in the air. That's what most people know it for.
Yeah, and also there's a lot of there's more CO2 in your house than anywhere else if you shut the doors, correct?
Yeah, that makes sense since we breathe it out. All right, we're done with the content for today, so I'll stop recording here, and then